With this equation, it says that every 15 seconds, half of the chemical A is gone. So at time equals 0 seconds, there are 30 grams of that chemical A. Okay, so I've got that part of it. What is the next time and amount you know that we can put on this table? Because every 15 seconds, half of it has decayed, dissolved, evaporated. It's gone. That's, chemicals work that way sometimes, right? So Margaret, what else would you know next? 15 seconds, there are 15 grams. 15 seconds later, we have half of what was there before. Coincidence that those two numbers are the same. Now can we put the next line in here? What is the next time and number of grams that you would know? Quick turn to your friend. Do you know the answer? Let me give you just like a very short 10 seconds to see if you can evaluate that.
I could be wrong. Because every 15 seconds, half of the chemical I think that's left, and so the air is going to stay.
All right, time's up. Time's up. I agree with comment over here. Like it gets loud pretty quickly in here. 30 seconds, 15 seconds later, how much do we have left? 7.5, which is half of what was before it. Let's do it again. 15 seconds later is 45 seconds. And then half of what was there, half of that would be 3.75. I'm going to do this one more time. What is the next time on here? 60 seconds. What's half of 3.75? Right, there we go. Okay, so this is what's happening with that chemical A and how it is decaying. So if I want to know how much of the chemical is left after 60 seconds, I could do this a few times, and I know there's 1.875 grams left. Still a little bit, but not very much. If I want to know at 20 seconds how much is left, I know it's somewhere between 15 and 7.5 grams. I just don't know exactly how much. And for that, we're going to write an equation. This is an exponential decay model. So we're going to say A of t is equal to A e to the b times t. If I scroll back, we had these general formulas yesterday for exponential growth and decay. It looks something kind of like this, where we have E as the natural base. What do these other letters in here mean? Well, A is the amount you have after t time, units of measure like minutes or seconds or hours. Little a is the initial amount you have invested. E is the number E. It's on your calculator. B is what we're going to try to find right now. That is going to be the decay rate. And since it's decaying, we expect B to be negative. And then T is the time in seconds. Yeah, seconds. Okay, so let's plug in that information. That information, they actually have three numbers up there that are going to get plugged into this equation. What goes in for A of t? Hard question. Let's go to the next one. What goes in for little a? 30. That's the initial amount. Times e to the b, which we're trying to find. What goes in for t? 15 seconds. 15. So 30 grams is the initial. Every 15 seconds, the amount that's left is half of the original. Okay, so if the original was 30, what's going to go in over here? 15. So I'm taking that information, plugging it into this exponential decay model. And in this equation, the only unknown right now is B. We need to solve this for B. And we've done a few of these problems. The goal is to get to B. What's the first thing you would do to both sides to start getting B by itself? Divide by not just 15, but 30, because that gets us closer to B by itself. Divide both by 30 even. 15 divided by 30 is 0.5. And I'll tell you, it's no coincidence that this number comes out to 0.5 or 1/2, because half of the chemical is decaying. Like, that's why this is really 1/2 right here. That equals e to the 15b. Like we've seen in a lot of these other problems at this point, it's kind of stuck. When it's stuck, that's when you convert. Log base E, so ln of 0.5 is equal to the exponent of 15b. This equation is almost solved for b, just a little bit more. Divide both sides by 15, so you have the ln of 0.5 divided by 15 is equal to b. Evaluate that on your calculator. This is definitely a calculator needing problem. The ln of 0.5 divided by 15. I got negative 0.0462. I'm going to write down that number, but it is rounded. I really don't want to use rounded numbers unless I really have to. We'll see if this comes into play later on. But for this part, it says write the formula for A of t. All right, so I have enough information to say that A of t equals 30. That's little a. That's the initial amount. E to the negative 0.0462. That's the b value times time. So this is our general formula for this one. If I want to know how much of that chemical A is left after like 5 seconds, I could plug 5 in for T. If I want to know how much of that chemical is left that hasn't decayed yet at, like, say, 50 seconds, I could plug 50 in for T. So I have a nice equation that can take me directly there. Part B says, determine the number of seconds it will take for the amount of chemical A to reach a safe level of 3 grams. So read it again. We're going to use that equation that we just wrote. The question is, where does this 3 grams get plugged in? There's A of t, 30, which is a number, E, which is a number, negative 0.0462, which is a number, and T. So the question is, where does the 3 grams get plugged in? Let me give you a quick 5 seconds. Can you share your thoughts with your friend again? Just 5 seconds, though. Go. All right, ready? It gets plugged in for A of t. Did we get that? Like the amount you have? So 3 is equal to 30 e to the negative 0.0462 t. And the goal here is to solve for t. The question is how many seconds it's going to take. Well, now if we can solve this equation for t, we know how many seconds it's going to take. Now, if I was stuck, could I venture a guess? I don't think anyone's done with this problem yet. Like, about when do you think this is going to happen? Look at the table we made before. Emma? Right in between these, right? She said about 50 seconds because at 45 seconds it's here. And just a little bit later, it should be somewhere between those numbers. And she's saying it's pretty close to 45, closer to 45 than 60. I think that's a pretty good guess. About 50 seconds seems like that would be a reasonable answer to get for this one. All right, let's see by doing the work if we're going to get an answer close to 50 seconds. And we've solved some problems like this before. What's the first step in getting this one solved for t? Divide by 30. Divide both sides by 30. We get 0.1 equals e to the negative 0.0462 t. Great, simplified it a little bit. Now it's stuck, so we take the natural log. So it's log base e ln of 0.1 equals negative 0.0462 t. And one more step before I touch my calculator. How about divide both sides by that? So t equals the ln of 0.1 divided by negative 0.0462. Now to my calculator. ln of 0.1, small number, divided by, and here is a way to keep it precise. I could type in negative 0.0462, and since that negative 0.0462 wasn't the last answer, I'm going to scroll up and grab it so it can at least get all of these decimal places, and keep it more precise without having to type all of those in. And it's telling me 49.8 seconds, which is so close to the prediction we had just a second ago. Remember, she said it's about 50 seconds by looking at the table, and that's pretty accurate. About 49.8 seconds. That is when the amount of chemical A will be below 3 grams. As far as what we're considering to be very significant in this final section, it is these half-life problems. A lot of the half-life problems are dealing with radioactive decay. This is dealing with a different kind of chemical reaction, but it's still this idea of something decaying every so many seconds. I'm going to skip over this one. Go down a little bit further to here. Let's test your chemistry. Yep.
Are we getting these equations?
No. No.
Okay.
No. All right. So there are 6 isotopes, 6 radioactive isotopes here. Anybody know what number 25, what this one is? 226 Ra? Radium. Okay. How about the next one? 14C? Carbon 14. How about this one? Potassium is K. I don't know. Maybe palladium. Pu, Am. Anybody know any of these? I think Am is americinium. I'm not positive, but americinium. Okay, 25 through 30. How about Rosa? Pick one. 25 through 30. Which one do you want to do? 26. Okay, so 26. We are told the half-life for carbon 14 is 5,730 years. Question was asked, do we need to know these formulas? You need to know that it is exponential decay when you're dealing with half-life. So it's going to look something like this. Y equals AE to the BX. B, I expect to be negative because it is decaying. I need to understand what these values represent. Y is how much you have at the end. A is the initial amount. E is E on your calculator, 2.718. B is the decay rate. Again, that should be negative. It's decaying. It's decreasing. And then X would be the time. So I'm taking this example right here and using this idea of the half-life of 5,730 years. So initial quantity 3, E to the B I don't know yet, times X. What's going to go in for this X? I know I have X written here. It could also be written as T for time. And that's the 5,730 number. So since the half-life is 5,730, that's why I'm putting 5730 up here for X, which is the time value. So initial amount, E to the B, T or BX. What is Y equal to? Say it again. I don't see 1.5 written over here. How'd you get that? Half of 3. Because it's half-life. Half of it, half of the 3 is 1.5. So we need to solve for B. And the first step in all of these kind of half-life problems is to divide both sides by the original amount. The original amount is 3, so divide by 3, divide by 3. And what is 1.5 divided by 3? 0.5. It's half-life. This is half. 0.5. 1/2 equals E to the 5,730B. Do you know what to do next? Seen a couple times already today. Take the log base E of 0.5 is equal to the 5730B. So B equals the ln of 0.5 divided by 5,730. Pretty small number, I'm assuming. Okay, so there's the B value. I'm writing it down. More importantly, it's still in my calculator because we still have to figure out this last column. How much of this 3 grams of the radioactive isotope of the carbon-14 is going to be left after 1,000 years? So y equals AE to the BX. Y equals, what is the A value here? 3, the initial amount. E to the B, that's in the calculator, times X. What is X going to be? That's the 1,000 years. So for the first part, we plugged in 5730 rather than 1,000. We plugged in 5,730 because we wanted a half-life. Half of this is left after that amount of time. Now that we figured out the rate of decay, I want to know what's going to be left after 1,000 years. So in my calculator, these are all numbers. I'm just going to go start plugging them in. It is 3 e to the, and I put B in my notes up here, but B is the last answer, so I can hit second answer, and it's going to grab all of those decimal places times the T, which was told to be 1,000. And it looks like we have 2.658. 2.658 grams of this are left after 1,000 years, which I think makes sense. If half of this decays in 5,730 years, then in only 1,000 years, you're not going to be taking half away. You're taking away less than that. That's why you still have like over half it left, 2.658. Not much has decayed by that time.
Why did they say half-life? I don't think they say life.
So if, let's say someone is standing right here, and he has hair that looks like this, with a mask on, and he's walking towards the wall. Let's say that every hour you walk halfway to the wall. So let's say right now you're 16 feet away from the wall. How long is it going to take you to get to the wall? Right? So like in 1 hour, you're half, and then you're half, and then you're half. But like you're never going to get there because you're only ever going half of the way there. So the question was, why are you using half-life? Why don't you use the whole life? It's the same idea. It never actually goes away. It's just decaying some more, and then some more. But it never actually goes down to 0 because it's only decaying by half. You could do a quarter life or a third life, but the half-life is the easiest to use. So half-life problem, and then we had this half-life problem from yesterday. I know they're kind of long. If you look at the work for any one of these problems, and there's quite a few steps that are involved in those. But that's the one new thing out of this section that I need you to make sure you understand how to do going into next Tuesday's test. I want to do one other problem right now because on the quiz, there was one problem that I think we struggled with. Yeah.
So when you're trying to find the B, do not make it negative because that's the exponential decay.
Yeah, so like in the notes, let me scroll back. I think I know what you're asking here. For exponential decay, it's written like this for decay, like that for growth. And they're saying both of those are B is greater than 0. If B is greater than 0 and you plug it in, it ends up being negative. Well, I don't like using this. I'd rather say y equals AE to the BX where B is negative. This is saying the same thing as that, but to me this makes more sense where B is a negative number. And because it's decay, that's why it's going to be negative. All right, so one problem that I saw we struggled with on the last quiz was something kind of like this. Let's go with 5 to the x plus 2 equals 8 to the 3x, just 3x. Goal is to solve for x. This would definitely be a calculator problem. I wouldn't expect you to get a decimal answer without using a calculator. There is a lot of calculations we can do to get to this point, but we're going to have to use the calculator eventually to finish this one off. It looks like this. It's an exponential form, and a lot of time in exponential problems, we convert. We're stuck. We convert, get it into log form. The problem with this one is both sides of this are already in exponential form, so there's not an easy conversion to put it into log form. So the other thing we can do is just straight up take the log of both sides. We could take log base 10, we could take ln, we could take log base 8, or we could take log base 5. It doesn't matter. Any one of them will get us to the same correct answer. I usually take log base whatever's on the left. Doesn't have to be that. That's just what I generally do. So in this equation, take log base 5 of both sides. And then can you simplify that a little bit? What happens when you take log base 5 of 5 to the something? So this stuff all becomes 1, and the only thing we have left is that exponent of x plus 2. On the other side, I would move that 3x out front because exponents can always be kicked out front. So it's 3x times log base 5 of 8. And so from first step, we took the log. From second step to third step, the left side at least simplified down by quite a bit. Here's where we're at. I'm going to just shift on you a little bit here. What if I had a problem and it was 4x plus 7 equals 8x plus 3? What would you do in this equation to solve for x? I think we'd probably subtract 4x from both sides and probably subtract 3 from both sides. You're getting all of the x's to one side. You're getting all of the numbers to the other side, so you can isolate like that. Right? You've done a lot of problems like that in Algebra 1 before. If there are variables on both sides of the equation, get them all to the same side so you can combine them. And that's essentially what we're going to be doing next. On the left, there's already an x, but then I'm going to subtract this from both sides. So minus 3x times log base 5 of 8. That gets it off of the right side. I subtracted it over there, so I subtracted on the left. Also, while we're doing this, let's subtract 2 from both sides to get the non-x terms to the other side. It's just like I did over here. Unlike that problem, though, is I can't combine these easily. It's not like 8x minus 4x is 4x. This is a little bit more involved. So this is when we look at the 1, 2 terms that are over there and factor out that greatest common factor, which is an x. Factor an x out of both of them. Inside the parentheses, then we'd have 1 minus 3 log base 5 of 8, and this thing is equal to negative 2. So factor the x out. That gets us down to this green, and now we almost have x by itself. I don't want this big blob attached to the x. Right now, this is all multiplied by the x, so how are we going to eliminate this from the left? So you could put that up there. You could call this 8 to the third. Like that'd be fine. Like you wouldn't have anything out front. This would just be a bigger number. That'd be fine. But how are we going to get this whole thing off of here? Divide by it. Divide by this. Divide by this. And the left side is x. On the right side, you already had a negative 2. Now it's divided by that 1 minus 3 log base 5 of 8. I like the idea of maybe putting this up here and calling it 8 to the third, or leaving it out front. It doesn't matter. But at this point, you would go to your calculator and evaluate that. Now, using your calculator at this point, I would recommend alpha y equals, choose n over d, and now it already looks like a fraction. Some of you had problems putting things into your calculator. By doing this, I have a numerator and a denominator. My numerator is negative 2. My denominator is 1 minus 3 log base 5 of 8. Oops. out, Will. Alpha y equals. I chose the wrong base. Wow. $6.849. Nope. My goodness. Can I type this correctly? How about 0.695? -2 over 1 minus 3 log base 5/8. I think so. So today, half-life problems. Think about how you're setting those things up. And then a little bit of review on solving these kind of problems, these challenging problems, which take a little bit of space, take a little bit of time.